Hello! In the previous videos you've learned a bit about cellular automata, and you've also seen examples of different types of neighborhoods, more specifically the Van Neumann and the Moore neighborhood. In this video we're going to talk about edge conditions or boundary conditions. So suppose we have an 8x8 grid and cells that are in the middle, like this red cell, they've got lots of neighbors. But the problem becomes what happens for cells that live on the edge. For example, this upper corner, it only has 3 neighbors, and so are we going to come up with a new rule for our edges? Are we going to somehow connect one side of the grid to the other? And so that's the whole topic of boundary conditions. Right, so there's 4 boundary conditions that we're going to talk about. The first one is no boundary. So this assumes that space is infinite and that you will never hit a boundary. Very common, you'll see periodic boundaries. So the idea here is that the left and right edges wrap around and the top and bottom edges wrap around, and this forms something called a torus. So imagine this were your grid, all right, and the top edge here is colored in red. And so we're going to take that top edge and we're going to wrap it around so that it makes like a tube or a sausage and meets up with this bottom edge. So if you connect those 2 edges, you'll have a hollow cylinder. And then once you have that hollow cylinder, let's take this blue right side and connect that end of the cylinder or that end of the sausage if it's flexible, right? Think about taking 2 ends of a straw maybe and putting them together. So it makes like a donut shape, which is called a torus. Right, so here's a picture. So again, the top edge meets with the bottom edge, and that would make this tube-looking creature. And then we would bend it around, right? Take the blue side and connect it around, and then you get this torus-looking shape. And if you're thinking about that still, you might want to take a piece of paper and try it, or a straw, or something flexible, even a shoelace you could imagine, and try to make that shape. Right, so that's pretty common, and we will often see that. So that means that a cell on the right-hand side, if we're looking for its neighbors, some of those neighbors would be in the interior of the cell, and then the other neighbors, we'd have to jump way over to the other side of the grid to pick those up because, again, we're living on a torus. The third boundary condition that you might see is something called cutoff boundaries. So the idea here is that edge cells have no additional neighbors, and you would need to come up with some different rules to accommodate for this. So for example, if you look at this corner cell, it really only has 3 adjacent neighbors, and if you're not connecting the edges like in the periodic boundaries, you're going to have some other rule, like how are you going to deal with just 3 neighbors, because all the other cases have many more neighbors than that. And then the last type of boundary condition that you might see is something called fixed boundaries. And in this type of condition, the edge cells never change their state. They just stay whatever they are, and that's how they remain for the whole simulation.